Hey, good morning, good afternoon, or good evening, depending on where you're joining us from today. And welcome to today's Game Developer webinar, Maximize Android Game Performance, ARM Tools for Monitoring, Reporting, and Optimization, sponsored by ARM Inc. and broadcast by Informa. I'm Alyssa McAloon. I'm the editorial director over at GameDeveloper.com, and I will be your moderator today. And we have just a few quick announcements before I hand things over to the expert. Today's webinar is designed to be interactive. You'll notice, let me get these instructions up for you. How about that? Today's webinar is designed to be interactive. You'll notice a dock of widgets at the bottom of your screen that will let you learn about today's speakers, download resources, share the webinar via social media outlets, interact with today's content, and participate in the Q&A session that takes place at the end of our presentation. Quick tip, feel free to add questions to the Q&A section as we go throughout today's presentation, and we'll discuss them at the end of the show. The slides you see on screen right now will advance automatically throughout the event. And you may also download the content resources via the resources widget on your screen. One quick thing though, toward the end of our webinar, we will ask you to complete our survey. Please take a minute to fill this out before you leave us today, as your feedback does provide us with valuable information on how we can improve future events. And last but not least, if you're experiencing any technical problems whatsoever, please click on the help widget found on the bottom of your screen, or pop that question into Q&A and we'll help you one-on-one. So now let's introduce today's speaker. Joining us today to talk about Android game performance and development is Pete Harris, the Technical Product Director and Distinguished Engineer at ARM Inc. Pete, off to you.
Super, thank you very much. So, welcome to this talk on maximizing game performance. We'll look at ARM tools for monitoring, reporting, and optimization of software and graphics running on Android devices. In this talk, we're going to look at three sections. One is going to be a look at what a mobile system looks like, what makes that an interesting optimization target, what are the key things that really you should be thinking about during optimization in terms of concepts and the kind of mindset that you want to take into it. We'll look at ARM Performance Studio. This is our library of free of charge performance tools. What's in the bundle? That's going to be a very whirlwind tour. There's an increasing number of tools in the bundle, so they each get one slide in about 1 minute. But then we're going to go and deep dive into two case studies. One looking at software optimization with our Streamline profiler and how you can get some kind of microarchitecture feedback from the CPU about how to optimize things. And one looking at rendering optimization with one of our new tools called Frame Advisor, which we released at the end of last year. So hopefully there's a bit of something for everyone here. And yeah, questions very welcome at the end. There will definitely be more we could talk about. So let's start looking at an introduction to mobile systems. So a mobile phone is a system on a chip architecture. So you have all of the processing logic on one silicon die, maybe 2 or 3 chiplets that are side by side. And then on top of that, you stack the DRAM memory and the flash storage. So all of the parts that you would consider to be a computer would be somewhere underneath the ARM logo on the motherboard there. This is great for manufacturability. You can just drop this package onto the motherboard and you're pretty much ready to go. But it does mean that all of the kind of heat generating components are in one place in the device, right? And every watt of energy you put into this to drive the electronics is energy that comes out as thermal waste that we have to get out of the device. And by far the biggest challenge for high performance mobile is these are passively cooled devices, right? You'll have a heatsink, a thin heat spreader. High-end devices may have heat pipes that link that into the device case to spread the heat, but you're not talking, half a pound of copper and a fan. So the biggest challenge is you can only run these as fast as you can passively get the heat out of those devices. And users make this difficult, right? You get smartphones in rubber cases to protect them. That's a great insulator to keep the heat in the device. You may have users in warm countries, so the same device may have a different thermal profile depending where your users are in the world. So this is a thermally constrained optimization problem. We have lots of CPUs, we have lots of memory bandwidth in a high-end device, we have a big GPU. We cannot afford to run all of those flat out at their peak performance all the time. So it's really about balancing the performance across those so that your overall sort of workload fits inside that thermal budget. And it's a very holistic system when it comes to optimization. You may find you're kind of notionally GPU bound, right? That's your dominant workload, but actually reducing memory bandwidth or reducing CPU load may actually help performance, because you free up thermal budget, you can run the GPU a little bit faster, potentially. So you have to optimize this as a very holistic whole, not treat it as individual components. And that's quite different to optimizing for PC or console, where you have active cooling and the individual parts of the system can always run at their peak performance. What's inside one of these SoCs, at least in terms of the main compute subsystem? So we have a memory bus that links everything together, and you will have a variety of CPU cores. And for modern ARM systems, there's normally 3 different types. And typically for an Android phone, you'll have 8 in total. The small cores give you the best energy efficiency. The big cores give you the best single-threaded performance. And the OS can load balance where this workload ends up. And typically, you'll only have 1 or 2 of the very big cores, maybe 4 or 5 of the smaller cores. And this is purely because you can't power 8 big cores inside that power budget. All processors need data, so there'll be a memory controller talking to the DRAM. And increasingly, for mid-end mobile upwards, you will have some kind of system cache sitting between the processors and DRAM. And it's not a huge system cache compared to PC, but 4, 6, 8 megabytes is getting increasingly common. That's still far smaller than your frame working set for graphics rendering. High-end games maybe a few hundred megabytes per frame of data, but it's big enough that we can start buffering some of that traffic going out to DRAM. And the reason this is so important is that touching DRAM is one of the most power-hungry things your application can do. So for LPDDR5, the latest mobile memory technology, at its kind of optimal power efficiency, it's somewhere around about 80 milliwatts per gigabyte per second. So if you're using 25 gigabytes per second of memory traffic, you're using about 2 watts of your overall power budget just to power the DRAM, not any processors running, just DRAM and memory controller and memory bus. So you will see high-end smartphones being advertised with 80 gigabyte per second peak bandwidth capability. If you do the maths and you work out how much power that's going to use, that would be 6 watts. You couldn't sustain that peak bandwidth every second throughout your game. So high-end devices with those very high bandwidth numbers give you small periods of burst bandwidth within a frame. So you might have a part of your workload that's very heavy. You can complete that nice and fast, but it's not designed for running sustained max bandwidth for long periods. You will overheat your device. Because memory is so expensive, optimizing for memory bandwidth is one of the most important things you can do, especially for graphics, which is a very data-heavy kind of processing discipline. There's a GPU, obviously generally a big processor, and the diagram's deliberately large here. We're a nice data parallel processing domain. You can put down more shader cores. The implementation parallelizes for you. So generally you benefit from silicon area without the application doing a huge amount. So high-end designs can have a much bigger GPU spending quite a large amount of silicon area on it, because you will see the performance uplifts. There will be a display controller or a display processor unit, a DPU, and this handles getting the completed images out to the window surface. And the reason I call it out here is that for mobile systems, the GPU and the DPU come from different vendors. They're not like a monolithic graphics card where everything comes from that vendor, for example. So the capability of the display controller can vary from SoC to SoC. And in particular for Vulkan, you need to be a little bit careful how you feed it with swap chains to avoid workloads falling back onto the GPU. And the reason that happens is the display processor is a real-time processor. It has to hit scan-out deadlines for the display or you get screen corruption. So if a workload is too complicated, too many layers, too much color conversion, too much rotation, you may find the OS compositor simplifies the workload using the GPU and then passes that composited image over to the display processor. So if you can, through again, through Vulkan especially, you don't want to give the DPU things that might fall back. So just one to watch out for, but we won't talk about that one much today. In terms of the kind of underlying physics of a mobile device, clock frequency really matters. If you've ever looked at a processor efficiency curve, you'll have seen graphs like this. So we have power consumption up the vertical axis, clock frequency as a proxy for performance along the horizontal axis. And the most important thing you'll note here is that the graph is not linear. It's getting less efficient as you increase the clock frequency. And this is because energy for a transistor toggle is proportional to voltage squared. We have to increase the voltage to make the transistors toggle faster. But you get this square law kicking in terms of energy. So if you're a PC hobbyist, and when I was a teenager, I loved overclocking my PC. So you're used to it going up and having to put a bigger heatsink and whatnot to cope with the overclock. The good news for mobile is it also works in the other direction. If you can underclock and reduce voltage, you get that V squared saving working in your favor. So optimization for mobile is often about trying to simplify the workload to the point that a system can start dropping clock rate, and you get that power curve working in your advantage rather than the other way around. The other part is bandwidth matters, and ARM's been saying bandwidth matters for years. It's always been very expensive to do compared to logic, but proportionally it's getting more expensive over time. So this graph, the green line is showing the kind of semiconductor efficiency of logic gates over the last 10 years. And it's a PowerPoint graph, don't take this too literally, but roughly an order of magnitude energy efficiency over the last 10 years from silicon process alone. So going from 32 nanometer down to 3 nanometer on the silicon side. This is ignoring processor improvements, like we build better GPUs, we build better CPUs. That's an extra kicker on top of this. But just the physics is giving us about 10x due to silicon process improvements. If we look at the same graph for bandwidth, we have it does improve, but it improves much more slowly. So we get a new major generation of DRAM about every 3 years, and each generation gives 20-25% uplift over the previous generation. So if we're 10x more efficient on logic, we're 1.7, 1.8x efficient on DRAM. So proportionally, you can now do far more maths per byte of memory access than you could do 10 years ago. So this just reinforces the memory is expensive, and it's really, really important that you optimize your data access, not just your shader code. In terms of like things to think about when you go into optimizing an application, obviously we're here to talk about profiling. I like this quote from Peter Drucker: efficiency is doing things right, effectiveness is doing the right things. He's a management consultant, or he was a management consultant. And it's not often you find engineers quoting management consultants. But I really like this one. I've done developer relations for Mali for almost 20 years. And a lot of times you go into helping a developer, and the first question is, how do I make this shader faster? Right? How do I tune it to save a few instructions? Take a step back, right? That's efficiency. But did you need to write the shader that way in the first place? Did you need to evaluate that shader that many times? So always take a step back, look at the bigger picture, worry about effectiveness first, then worry about efficiency of what remains. So what might that look like when it comes to things to optimize? So effectiveness, I would say, starts with understanding the devices you're targeting and choosing an appropriate base configuration for your application. And by base configuration, I mean things like resolution, things like frame rate. Do you need to use HDR or LDR colors? Those are all things that if you get them wrong, it's very hard to recover later, especially if you decide you want to target a lower specification device with a smaller CPU or smaller GPU. Frame rate, resolution, color formats, that they all multiply together as you increase frame rate and resolution and color format. Your bandwidth goes up as a cube law. So it's very, very important to get those right. And if you get them wrong, it's very hard to recover later. Similarly, look at the algorithms you're choosing to target. So, do you want to use physically based lighting for everything? Do you want to use dynamic shadows for everything? Do you want to pre-compute shadows? Buy some representative devices, do some mock-ups, test the performance out, see what you can make fit, do some upfront budgeting, because again, it's easy to do that at the beginning. It's quite hard to rewrite things later. And then finally, avoid doing things that don't produce any visual output. It kind of sounds obvious, but this is actually really common. So, CPU side culling would be a good example, right? Draw calls being sent to the GPU, but they're behind the camera, they're behind a wall, or layers of opaque objects being sent in. And that's all work the GPU is going to need to at least partially process, right? We can't cull anything until we've at least processed some of the vertex shading, so we know where things are, and then we can cull them. By that point, you've wasted shading bandwidth, you wasted memory bandwidth. So being very aggressive on not doing things that you don't need to do is always where I'd start, right? The one thing faster than making something more optimal is simply deleting it and not doing the work at all. So for the efficiency side, you've tuned all of those things. Start with minimization rather than performance, right? Making things smaller, whether it's data size or vertex count or triangle count for models. Again, doing less stuff is going to be faster. So start by doing less and then worry about fine-tuning optimization state as a later stage. Smaller is good. Similarly for texture data, make things small. ASTC gives a very granular set of compression levels that you can use. So can you squeeze the memory size down, make sure you're using mipmaps? Can you get away with simpler texture filters? Anisotropic is very nice. It solves a whole load of problems. It does cause a lot more bandwidth because you pull from more detailed MIPS. So again, just tune what you think you need. And for all of these, base it on the visual impact on screen. You can language lawyer and quality lawyer discussions until the kind of cows come home. Really just look on screen on a real device and go, okay, if I change this setting and I make it faster, can I visually see the difference? In reality, a lot of the time, the answer is no. And you may find something that's quite a lot faster that just isn't, the more expensive technique isn't pulling its visual weight. And then finally, look at optimizing shader code. It's always the last thing to do, right? Optimizing shader code is hard. And even if you manage to find some good optimizations in shader code, it's probably only going to buy you 5–10%. It's everything else that comes earlier where the bigger gains are. So in summary, for this one, don't do things you don't need to do. Deleting things is always the fastest option. Make things smaller first, whether it's data size or number of things you're processing, and then worry about making the remaining ones fast as the last step. So now, lightning tour of Performance Studio. I just want to overview what's in the studio and the kind of tools that are there. This is going to be awfully brief. If you'd like to get more information about any of the tools, feel free to grab us offline or look on the ARM website. I can't do them all justice in this one webinar. So ARM Performance Studio is our set of performance analysis tools for ARM CPUs and the Immortalis and ARM Mali GPUs. They are tools designed for application developers. They're not designed for OEMs, building devices or silicon manufacturers. They do use them as well. They are designed to be usable on consumer devices. You don't need root, and they're free to access and download. And they cover everything from graphics profiling, software profiling, through to graphics debug, shader analysis, and we have a number of open source libraries that I'll briefly mention as well. So you may have come across our tools before under the ARM Mobile Studio brand. They are the same thing. We've added support for ARM Linux, so you can do embedded IoT and cloud server optimization for the CPUs. So the Mobile Studio name didn't make any sense anymore. It is just a rename. It's still free. It does more stuff. Don't worry. So if you're used to Mobile Studio, go download ARM Performance Studio and you're in a good place. The workflow we try and encourage is a three-stage workflow. One sort of starts with monitoring. So how do you stay on top of performance during development with the kind of modern CI DevOps type workflow, right? Profiling shouldn't be something that you do at the end of the project, or have a tech artist do manual profiles once a month, right? It's expensive. It's a really expensive use of human time. So automating profiling, get it into monitoring, get regular reporting, do optimization when the reporting and the monitoring finds a problem. And that's when humans should be involved. You shouldn't be using expensive human time to just run profiles. So we try and encourage this, and we build tools that can support these different parts of the workflow. So we have a tool called Performance Advisor. This is based on our Streamline profiler, which is the same tool you'd use for interactive use, but you can run it in a headless mode, in a Jenkins job, for example, and capture performance counters from CPU, from GPU, while your application's running. And we can analyze that and give you feedback. Did different parts of your game hit the frame rate target? If not, why not? Was it fragment, vertex, CPU? So, and it tries to give some of the headline KPIs. So GPU memory bandwidth, number of draw calls, number of render passes, number of shader cycles of different flavors. It's not trying to be a fully detailed profiler. These reports are designed to be quick. You can read them in a couple of minutes. If these find a problem, you're going to need to go and pick up the full profiler to open the data and go and deep dive. There are two outputs from this. One is JSON data, so you can import it into a NoSQL database for dashboard reporting, so your QA team can just take the data and plot it and track trends. Or you can get these web-based HTML reports where you can just publish them to your team's internal microsite and get a report every night for each test device you care about. Streamline itself is a sample-based profiler. It has extensive support for CPU profiling, which we'll look at a bit later, GPU performance, lots of performance counters for the ARM GPUs, queue scheduling for the ARM GPUs, and it's designed to be low overhead, right? As a sampling profiler, it's maybe 2-3% CPU load impact on the application, very, very minimal impact on the rendering time on the GPU itself. So it's a great thing. You can just drop in and profile your application and get feedback about what the hardware is actually doing on particular devices. We have a new tool called Frame Advisor. So this is a graphics API frame profiler. So it sits between the application and the graphics driver, pulls out the API calls, and as we'll see a bit later, we'll talk about this tool in more detail. It tries to give feedback around why particular models or particular bits of your application aren't being as efficient as they could otherwise be. It's a new tool. It definitely isn't finished. There's a load of features we want to go and add to it. So if you use it, we'd love to get some feedback. Is it helping? Is it not helping? Does it work? Does it not work? And give us feedback and help us prioritize the roadmap. And I'll explain how you can do that later. We have our own build of RenderDoc. So RenderDoc's sort of the de facto graphics debugger, especially for Vulkan. And the feedback from the industry has been, we don't want another vendor debugger. So we are collaborating with Boulder upstream to add improvements for RenderDoc for things that we support in the GPUs. We're currently focusing on Vulkan ray tracing, so RayQuery and the full ray tracing pipeline support. And we're releasing our own builds because we can release our changes a little bit sooner, but our plan is to be good citizens and upstream as much of that work as we can. We don't want this to be an ARM fork that goes off into the sunset and diverges from the RenderDoc that everybody's used to. So watch this space. We are working with Boulder on the ray tracing upstreaming now, so that should happen soon. We have Mali Offline Compiler. This is one of the unsung heroes a little bit of the tool suite. So it's the driver shader compiler, but as a desktop binary. And you can compile your shaders through that, both source shaders for OpenGLES and SPIR-V shaders for Vulkan. also OpenCL as well if you're on Linux or macOS. And it gives you static analysis about the performance of that shader code, at least as far as the compiler can see it. So you get syntax feedback if you've made a syntax error. You get performance feedback about register usage, thread occupancy, anything you're doing in the shader program that might cause some of the fixed function hardware to change its behavior, like early or late ZS testing. And you can use this to kind of early test performance on any Mali GPU that the tool supports, which is still everything back to the Midgard GPUs. So Mali T720 is the oldest GPU we support in the tool, which is now, I think, over 10 years old. So you can generally compile for any of the devices that are still shipping on the market today. Again, this is designed for CI, so it can output JSON reports, and you can dashboard trends in your shaders over time. And we know of multiple game studios who run all of their shader code through this as part of their nightly CI testing a variety of different GPUs to check that it's going to give them the consistency of performance that they really want to achieve. We have a number of open source projects outside of Performance Studio that my team maintains. We have the ARM ASTC encoder for texture compression on GitHub. So if you like compressing textures, you can go there. Nearly all of the game engine compressors for ASTC are now using this as the backend. So it is pretty much now the de facto compressor for the mobile industry. We have Harbor Counter Pipe. This is a library that gives you access to all of the GPU performance counters as you would find them in Streamline. So there's no gatekeeping here. Our tools, the data is available to anybody else who wants to build in-application tools. As of last summer, that library also now automatically computes expressions. So you can request things as higher level metrics, and the library does the maths internally, combining multiple hardware counters. We have libgpu-info. This is a library that gives back configuration information about the Mali GPU in your device, how many shader cores, how many caches, how big are the caches, those kind of things. So you can query, ballpark the performance configuration that a particular device is going to have. That information is also available through some Vulkan extensions for newer drivers, so you don't need to use the library on the latest GPUs. We also have some bindings for Unity, which expose Streamline event annotation bindings and software counter bindings as C# script callable functions. So then on to a couple of the case studies. The first one is going to look at software optimization with Streamline. So Streamline's a sampling profiler. We can find hotspots in your code based on samples. And we want to build a tool that is aware of the CPU microarchitecture. Obviously, we're ARM. That's part of the value we can provide. So why is a particular function a hotspot? Not just it's slow, but it's slow because that can give you some hints about what to go and optimize. So the basic software profile is time-based. So you get 1 kilohertz sample rate every millisecond. Take a sample of the program counter and the call stack. And you can use that to visualize your hot functions, and you can use that to visualize your hot cool paths. So this profile is telling you about time density, right? Where is the application spending time? And you can use this to pick the hot functions, but as a user, you're then left to your own devices to work out why is it taking time. Be nice if the tool told you. So in this case, we're going to look at this compute averages and does 3-component RGB function. And this is a real optimization that we found for the ASTC texture compressor, so it isn't a dummy case study. And so we have some code. It's not a very long function. This is the important part of it. It's computing the dominant direction through a block of texture data by comparing textures to the average value of the current block, and then accumulating them. And the first thing I would normally do for any profile is go and look at what the compiler's done, because sometimes you find the compiler's just generated junk code, and fix that first. But in this case, we can see the compiler's done a reasonably good job. We can see some branch greater than instructions in there. So it's a fairly close mapping of what the application shader code looks like. One thing Streamline can do is tell you where the samples land relative to the individual instructions. And so here we can see for what is otherwise a straight line piece of code, we see a very non-even distribution of samples. We can see a fairly high percentage of samples piling up just after the branches. And because of how the interrupts are taken for the event-based sampling, it's normally just after slow instructions. So just looking at this data, you immediately think, maybe the branch is something we care about. But wouldn't it be nice if we could get some data from the tool that could confirm that? So the other way you can do profiling is using event-based sampling. So for this profile, the CPU has a whole load of performance counters in it, and you can select different events to profile on. And rather than triggering a sample every millisecond, we can trigger a sample every so many hardware events. We get an interrupt from the performance unit, and that triggers the performance counter sample that we use. And you can choose which event you want to do your sampling on. Useful things would be things like front-end stalls, so iCache misses or lack of instructions to issue, branch mispredicts, L1 data cache or L2 data cache misses, TLB misses for the MMU. Right? Those are the kind of major reasons why code starts stalling for normal code. So let's go and do an event-based profile based on branch mispredicts. We think branches are a problem, so let's go and do a profile taking a PC sample every 10,000 increments of that branch mispredict counter. And if we compare the two, we have a function which is 12% of our runtime, so it's a hot function, but we can see it's 33% of our mispredicts. So it's a massive outlier, right? Ideally, very hand wavy. These should be about the same. They'll never be exactly the same. Not all code is equal in terms of branches, but the fact this is 3 times more significant for branch mispredicts than it is for runtime does tell you something about this being an unhappy function when it comes to branch prediction. So the optimization we applied here was just get rid of branches. Branches are fast on modern processors because of branch predictors. So the core learns the pattern in the software and uses that to make branches free. If you get a misprediction, you have to unwind the pipeline, and that can take 10 plus cycles on a modern core. So if you look at what the code's doing here, it's picking a small block of texels, 4x4, and comparing individual texels against the average color of that particular block. And it does it once, and then it moves on to the next block, which has a different selection of texels in it, and it's going to contain different data. So there's not a very predictable pattern here for the branch predictor to learn. It is trying, so this kind of code is naturally unpredictable for a branch predictor. So we're getting a fairly high degree of branch misses. How do you solve that problem? By not having branches. So most instruction sets have got the idea of a conditional select. You compute the if and the else and a mask, and then you basically pick which of those 2 answers you want, depending on the value of that of the mask. So you have to compute both the if and the else path, but you get rid of the branch. And on a modern core, say a branch mispredict is 10 cycles. Maybe you're issuing 4 instructions per clock on a high-end X core. So that's 40 instructions worth of stuff you could be doing while unwinding a branch mispredict. So generally for small things like this is a really good way to go and get better performance. This would be slower if the branch is predictable. So if you have a pattern that the branch predictor can learn, this may be the wrong thing to do. But for unpredictable branches like this is a really good optimization technique. Also helps on Intel as well for x86. So this isn't just an ARM optimization. So if we then repeat the profile, so say just with that one change made, we can see that our runtime drops from 12% to 7.5%. So a 5% optimization, that's really big. It's quite hard to find 5% optimization sometimes. And we can see that our branch mispredict percentage goes from 33% down to 9%. So it is still mispredicting, but it's now roughly in relation to the time significance of that function, and that's okay. That's about where we'd expect it to land normally. So you could repeat this with different counters. You could look at, say, data cache misses for the L1 or the L2, other reasons for stalling, and find similar kind of microarchitecture aware optimizations to help you really squeeze the performance out of those critical libraries on your CPU. And there will be more improvements coming on the software profiling side over the next 12 months or so. It's a current area of focus for us, so I hope to be able to share more improvements on this part soon. For the final part of this, I'd like to talk about Frame Advisor. So this is a new tool that we released at the end of last year in response to a lot of the sort of tech art teams in game studios we talked to complaining that a lot of the existing kind of graphics tools like RenderDoc, like some of our tools like Streamline, are really quite hard to use, and therefore profiling becomes something that only the rendering engineers can do, and that's quite a small team in most studios. So this is a tool trying to be a bit more accessible, providing higher level analysis than, say, RenderDoc or our older graphics analyzer tool. And the reason why we think this is really important is that ARM GPUs are tile-based. So we process draw calls as two pieces. We do the geometry processing for each image first, work out which triangles contribute to which screen space tiles. And then we fragment shade individual tiles to completion. That stays inside the tile memory. This is what gives tile-based GPUs really good fragment efficiency. But from a profiling point of view, the workload is for each render pass is two disjoint phases, a vertex phase and a fragment phase, or a binning phase and a main phase for the newer GPUs. But the single draw call that the application submitted is partitioned into little pieces scattered throughout that workload. So there'll be some vertex processing that happens first, and then depending where the triangles in that draw call end up, you'll end up with little bits of fragment shading per tile scattered throughout the fragment shading time. So what does the driver say when you ask, how long does a draw call take? You can't really answer it. Timer queries would just say, well, this draw call took the same amount of time as the render pass. So for tile-based GPUs, you can use timer queries to time render passes with some care, but it makes no sense to time draw calls. And so if you've got an application with 50 draw calls, which one's the most expensive? How do you optimize it? The hardware can't really give you the feedback. Draw calls don't exist as nice monolithic pieces of work to profile in the way they would for an immediate mode renderer. So the idea for Frame Advisor is providing a tool that can help bridge this understanding gap. So this is a static analysis tool. It sits between the application and the graphics driver in the same way that debug tools like RenderDoc do. And we know how the GPU is going to process a particular draw call. We can see the shader, we can see the input data. So we can put this through a very lightweight cost model and give you feedback about different aspects of the application. And for each draw call, give you targeted feedback about, why isn't that draw call following best practice, or are there things you can do to improve it? And because it's tied to a draw call, you know exactly what to go and fix. Whereas with Streamline, if you've got some high counters saying, oh, you've got lots of partial triangles in a frame, where did they come from? You don't know. You have to go manually investigate through RenderDoc or this kind of tool. So the goal here really is to make that kind of performance data and performance feedback far more accessible without needing to understand exactly how the hardware is working. It's worth saying it's a new tool. It's still in development. If you look at the feature set here and underwhelmed, is this all it's doing at the moment? Yes, but we have a team working on it. It's going to gain features fairly quickly, we hope, throughout this year. So again, if you have feedback about things that are good or bad, or things that are obviously missing, like shaders, for example, let us know. It helps us set the priorities for the team. In terms of what we have today, we have the render graph view. So we track the render passes that are inside an application. We see the attachment reads and attachment writes, and we can show you the data flow within a frame. So how are things related? are there things that aren't necessarily useful? So an example of the kind of problems that you can see here are floating render passes where the output isn't getting consumed in something that goes into the swap chain. So this could be redundant. You could just optimize it out and no one would notice. It may not be. It could be an async workload for the next frame. So there are some gotchas here where the tool can't see it. But for the most part, this would be something you may want to go and investigate. More commonly, you can find things being written back to memory that are never read within the frame. So here we have a render pass that's writing out a depth render buffer, and the application doesn't include an invalidate at the end. This is an OpenGLES application. So we're writing it out to memory rather than just discarding it out of tile memory, but there's nothing consuming it. So that's just a waste of bandwidth. You could save some power by optimizing that away. So just by inspecting this graph and looking at that data flow, you can very quickly find kind of redundant nodes, redundant writes that you can then go and improve. The second workflow we have in the tool at the moment is what we would call frame review. So you can step through the draw calls, you can see what the GPU did, you can look at color buffers, you can look at depth buffers, and you can see how the frame is being built up by the game engine. And I would say there's 3 useful things you can do. It's somewhat manual currently. We're hoping to automate it a bit more. But one is look at the mesh complexity in the mesh view. So you get the wireframe. Look at how many pixels it's actually rendering on screen, and you kind of, is that mesh complexity necessary for the number of pixels that are being covered? Especially on mobile, where you end up with a 6-inch display running at 500, 600 DPI. Single pixel triangles are really, really expensive. So, and you actually can't see that level of geometry detail on a screen anyway, because it's all so small. So can you reduce model complexity so that it's more aligned with the amount of pixels that particular draw call is covering? Are there duplicate draw calls? So here we can see a whole sequence of draw calls rendering these pillars in the background. They're identical models just being drawn one after the other. For a modern API, that would be a great chance to use instance draw calls and reduce the amount of driver overhead that you're generating on the CPU side. You may find that you have draw calls that, as you step through, don't seem to change anything, right? Because the draw calls behind something or off screen. If you've got a high percentage of those, that would be a good chance to go and review your CPU side culling. The final tool we have in at the moment is what we're calling geometry review. So we have content metrics, which give you statistics about each draw call. And there's a whole collection of statistics about the geometry efficiency in terms of how it's processed, how the index buffer is laid out, how the vertex attribute data is laid out. And we try and summarize this as really 3 things. One is the absolute values, so number of primitives, number of vertices, number of unique indices. It gives you a sense of how complex the model is. And then we have 2 efficiency metrics, VSE, which is vertex shading efficiency, and VME, which is vertex memory efficiency. For both of those, a score of 1 is good. You're only touching or shading what you need. A score less than that means that you're doing redundant work that is potentially unnecessary. So for vertex shading efficiency, you're looking at only shading indices that you actually want to use. You may find that you have gaps in your index buffer. Mali shades in groups of 4, so gaps mean that we'll end up shading indices that you're not actually referencing. So if that value is high, then you could compress your index buffer to remove redundant shading and data fetch. You may find you have duplicate vertices being shaded. So these are vertices that are different in memory, but have identical data values. So you could compress those into one physical vertex, re-index your index buffer, collapse it down again. And that can be quite common for use cases like shadow mapping, where you may have a shared position on a hard edge. For the full shader, you need 2 different vertices because one's got normals going that way and one's got normals going that way, for example. But for shadow mapping, you only need to know the absolute position. You could specialize a mesh for just shadowing, make it smaller, strip out redundancy, save some bandwidth. You may also find for shading efficiency that you're reshading the same index multiple times. So Mali has a post-transform cache for vertex shading. So we store positions we've shaded recently, especially for binning. And if you don't reuse that data for a long time in the index buffer, it's 2, 3, 4,000 indices away. By the time we get back round to indexing it again, that position data has been evicted from the post-transform cache, and we have to go and reshade it. So beware of reshading. So try and keep your index reuse close together in your index buffer. Memory efficiency is the same kind of thing, but it's looking at the number of bytes you're touching rather than the number of shader invocations that you're making. So the first problem is more about absolute size rather than efficiency. So do you just have too many primitives, too many vertices, poor index reuse on triangle edges? Is your vertex data per vertex just consuming too many bytes? So absolute numbers, could be perfectly efficient in terms of shading what you're using, but it's just physically large. Then memory efficiency is for what you're using or what you're fetching from memory because of DRAM access patterns and cache access patterns. How many bits are you actually using? So are you fetching unused vertices due to sparse indexing? Do you have padding in your vertex data where it happens to share a cache line? So each of these has a very actionable fix from the application. Finally, one thing I would say is it's really important to optimize your mesh memory layout for tile-based GPUs, and the goal here is avoiding redundant data fetch. So as far as I'm aware, all the tile-based vendors do some kind of binning pass first. So compute position, work out if it's a triangle we need to keep, put it through culling, only do the other part of the vertex shader for all non-position if that's a triangle that we need to keep. The traditional way of passing in data to the GPU is going to be fully interleaved. So you have a single array of structures. In this case, position, tangent, normal, texture coordinate for one vertex, and then repeated. When we do that binning pass for the position calculations, we'll go and fetch position first because we need it for position. In this layout, you end up fetching all the other data because it shares the same cache line as the position data, and DRAM wants to get access to whole cache lines. It's by far the most efficient way of touching memory. So for the triangles that are then culled, you fetched a whole load of data that you really didn't need. So a better way of laying out your data in memory is a packed stream of all of your position-related attributes, and then a separate packed stream of all of your non-position-related attributes. This allows position shading and binning to run efficiently. It's only going to fetch useful positions, and then whenever the GPU comes to process the non-position work, we only need to fetch the data for the 50% of vertices that survive culling. So this is really important, and again, not a Mali optimization, just a generally good practice mobile optimization. For this tool, so it's new. If you try it, you will find there are gaps in terms of features. We have a long list of ideas to go and try, whether it's adding compute and transfer to the render graph, whether it's better HDR support in the image view, render state analysis for blending, depth testing, stencil testing, and so on. Shaders are an obvious resource that's missing. Textures are an obvious resource that's missing. So there's a lot more to come on this tool. It would be useful to hear whether it's which bits you'd view as a priority if this is the kind of tool that interests you. We prioritize based on developer feedback. We're making releases every 8 weeks, so we can go from there. Let us know what you think. To give feedback, if you go to the ARM Performance Studio webpage, there's a feedback button next to the download button, and you can fill in a web form and send us anything you'd like. If it's something where we're probably going to need to get back to you, if it's a bug and we need a reproducer, please do leave us your email address. That really helps us. But all feedback is very welcome, and we do read it all, and we do change the roadmap based on it. Finally, if you'd like to sign up to our developer program, we have a Discord channel. We have YouTube videos that cover a lot more training material. So if you find the ARM software dev channel on Discord or YouTube, we'd love to chat with you. If you want to download the tools, they're on developer.arm.com/performance studio, and there's that and a collection of other learning materials if you sign up to our developer program. And thank you very much.
I think we'll jump right into the Q&A portion here and try to get through these in the time we have left. Thanks so much for that. That was very interesting, and I'm looking forward to chatting with you after the show a little bit. But now, for the rest of us, we will be moving on to the question and answer portion of our event. As a reminder, to participate in the Q&A, you're going to want to type your question into the text box located to the left of the presentation window, or click on the Q&A icon at the bottom of your screen. If our guest is not able to answer all submitted questions during today's webinar, we'll be sharing them with them after the show, so they can reply to you offline. So jumping right into it here, first question coming in. We have some applause coming in through the audience react feature, and that's very cool to see on the thing. Thanks, everyone. One of the biggest challenges my team has when shipping on Android is managing the number of device configurations we need to support. Do you have any suggestions?
Yeah, this is a common one, I think, especially for Android, because there's so many different OEMs shipping different GPU configurations. So you probably have an order of magnitude difference between a kind of entry-level phone performance and a top-end phone performance. So it is a wide range to span. I think the first thing for me really is research before you really start developing your game. It's much easier to set content complexity at the beginning of a project than try and fix it later. Especially once art's involved, it's really expensive to rework. So look at what your kind of low-end min-spec device can do, plan your core technology stack around that, and then work out how you scale it upwards. So a little bit of device research up front, and that may even go as far as building prototypes. Once you're into actually developing the game, I think automation, I would say, is the key. There's so many devices, there's no way you can manually test all of them. So tools like our Performance Advisor tool are designed to help take some of that pain away, have test scenarios that you can run and kind of regression testing on, put some effort into making those test scenarios reproducible. So if you run it over 3 nights, you're going to get the same output, and it's just shader performance or mesh performance that's causing the results to change. The cases where we see teams struggling is where they're relying on a very small sort of technical rendering team or tech art team manually profiling, and that really doesn't scale. So I'd say plan in advance and plan to automate.
Cool. We do have a couple of questions about different GPU and CPUs in here, so I'm going to try to group them together, and we'll get to everything if we can. Next one in here, how do you recommend profiling software running on the various big, middle, or little CPU types?
Yep. So this one's a challenge because I think Android doesn't make it easy to control by default. So kind of core library technology, my preferred way of profiling is actually to make a little standalone kind of native binary, not an Android APK, just a little standalone command line tool. You can run that from the shell on a consumer device and profile that individually. And Android's got the task set command, the sort of standard Linux one. So you can tell it to restrict running this to particular cores. And so you can force it to run on a big, you can force it to run on a middle, you can force it to run on a little, and profile it that way. It's going to see how it would perform differently on different types of core. So you can do that with our Streamline profiler. It does require a little bit of command line wrangling to run the application, but that profiling approach works fine.
Cool. I'm going to ask the other one dealing with CPU here. One of our audience members wants to know, are all the tools you discussed helpful for ARM mobile CPU or server CPU as well? I believe this question came in during the second section you were presenting.
Yep. So this is a very timely question. So the background of these tools is very much client, so smartphone, tablet, things with screens. We are working, one of the reasons for the rebrand to Performance Studio is to help target these at server, running the ARM Neoverse CPUs or equivalents. So absolutely, for Streamline as a profiler. One thing I would say is the current tool through the GUI for this release that you can get hold of today doesn't scale very well to 128 core server systems. The analysis time on the tool itself is quite slow. It works, but it just takes time to think. In the Streamline bundle, there is a collection of command line tools under a prototypes directory. There are some new tools we're designing for deliberately for server. That has a new data processing backend in it that's a lot faster. So profiling 20-30 minute workloads on Graviton is fine, for example. That is something that we will be merging into the GUI tool over the next 16 weeks. So hopefully by the kind of Performance Studio 2024.2 release, that's the current target, the GUI tool should be up to speed with the kind of number of cores you get. So we're not quite there yet, but imminently, yes, absolutely. These should be CPU profiling tools for Server 2. If you try them and have requests, please get in touch. That's something where we're putting quite a lot of effort over the next 12 months. So if you try things and have problems, we'd love to hear from you.
Yeah, exciting things to come then. Saw another question in here about on demand. This will be available on demand to watch after the broadcast. So be sure to tune back in if you missed the beginning of it. Jumping onto our GPU questions then, one asker says, I currently only have access to a device with a GPU from another vendor. Will your tools work on devices without an ARM GPU?
So the CPU side, yes, any ARM CPU is fine. Some of the microarchitecture counters, you'd need a ARM-created ARM CPU. We don't always have that definition file from other vendors. For GPU, it depends on the tool. So for our Streamline tool, the performance counters are us talking directly to our driver. There's no standard interface to go and get that data. So anything involving the hardware definitely won't work. We don't support Qualcomm performance counters, for example. Anything at the API level, so RenderDoc for ARM GPUs or Frame Advisor, the intent is that it should work. We don't test huge amounts of applications on other vendor GPUs. So you may run into issues if there's a particular extension that's missing in the graphics API, for example, that we're not modeling correctly yet. If you run into those issues, let us know. We're happy to fix them. It is something that we would like to work. One of the overwhelming bits of feedback we get from developers is the pain of having to wrangle half a dozen different vendor tools. So anything we can do to help reduce that would be good.
Oh, sorry, I didn't mean to cut you off there.
Nope,
well, I was going to say, I think you might have kind of answered our next question as well, but I'll read into it and let you tell me. So when Andres wants to know here, when profiling and optimizing on an ARM/Mali hardware, will the recommendations generally be applicable to mobile hardware? Example, ARM systems on non-Mali GPUs.
Yeah, absolutely. I think if we start giving people advice that's great for Mali, but 5% slower on other vendors' GPUs, we're going to burn a lot of developer credibility we have. So like 95% of what we do is generic optimization advice for Mali. It's about content efficiency, and that will help anywhere. There will be 5% that's probably going to be very specific to avoiding particular Mali bottlenecks or particular things that where we know there's driver bugs, for example. So we have some linting rules that we want to roll out that can help steer you around those kind of problems. But for those cases, we'd at least hope they're neutral on other vendors. Even if they're not helping, they shouldn't hinder. We don't want to be giving advice which is really good for us and terrible elsewhere. Like we know you guys have got games to ship, so
game development's hard enough, right?
Exactly.
So for someone at the start of this will be our last question. I'm going to always squeeze one in. I'm sorry for going a little bit over time here. But wrapping things up will be, how would you go about using the ARM Mobile Studio to help a developer establish an appropriate base config for their game? That might be a bit long for a minute question, but what's your minute reply?
I mean, I think we covered it a bit earlier around some of do some research up front, look at the devices that you want to target, build some prototypes. I think that's a really important thing that's often forgotten. So try the kind of techniques you want to run, try it on a representative device, profile it with Mobile Studio tools. Is it in the right ballpark? If you're within 10, 15, 20% of where you want to end up, great. That's the kind of fine tuning you can fix later. If you're 2x off, you probably want to take a step back and rethink. So I would say, again, it's sort of plan in advance, prototype, profile, and then use that to kind of make some design decisions.
Take advantage of the wonderful tools that are listed in the slide deck that people can download after the fact here too.
Absolutely.
That in mind, I guess, Pete, any final thoughts for our audience? Anything you want to share? One takeaway from today's presentation?
No, thank you for coming. I say, I enjoy mobile optimization. I like the kind of puzzle part of it, trying to get CPU, GPU, memory all working efficiently. I think the main takeaway for us is we're here to help you guys. We want game developers to be successful on mobile. So if you're running into problems with the tools, if you're finding features are missing, or you're running into tools not working, please do get in touch. We're very happy to listen to feedback. So thank you.
Cool. Thanks so much. And for those of you, we did have some questions we didn't get to today. Unfortunately, time is finite, but we will be sending these to the folks at ARM to go over and reach out to you with answers after the fact too. So stay tuned. And that is going to be all the time we have for questions today. Thank you so much, Pete. We really do appreciate your time and expertise. And thanks for our audience as well for participating in the Q&A and staying engaged the whole time. It was a wonderful show all around. So for those of you in our audience, within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. You can rewatch anything you might have missed, but also feel free to invite your colleagues or peers who might be interested in what was discussed today to that on-demand recording as well, and they can learn and grow. So the webinar itself, copyright by Informa. Meanwhile, the presentation materials are owned or copyrighted by Game Developer and ARM Inc., and individual speakers are solely responsible for their content and their opinions. All that being said, I'm Alyssa McAloon I'm Alyssa McAloon, and I'm running out of time to talk apparently. But on behalf of our guests and on behalf of ARM, thank you so much for your time, everyone, and have a great day.
Thank you.